In the last video, we had started with all closed intervals in my set AB, and we had specified length for all these things, S minus R. Then by simply combining such sets, we could arrive at many other sets. We could do it for all sets of these forms, open, semi-open, all subsets of AB. We could define lengths for these things, starting with just this. Then we could also do it for various unions of intervals. And eventually we could obtain it for the set of all rationals in AB as well as the set of all irrationals in AB. So we started with only the collection of all closed bounded intervals, and then simply by using union, intersection and complementation repeatedly, countably many times, we could arrive at all these different sets and could define the lengths for all these sets. The question is, how far can we go like this? Can we manufacture all possible subsets of AB using just closed bounded intervals and the standard set operations? No. The answer is no. It is not possible, but it is quite difficult to come up with a counterexample. That is, come up with a subset of AB that you cannot arrive at by just combining closed bounded intervals using these operations repeatedly. Now let us give this collection a name. Let script B denote the collection of all subsets of AB that may be created using countable union, intersection and complementation, starting with just the intervals. Or you may say just closed bounded interval, doesn't matter, because if you allow closed bounded intervals, then of course all open and semi-open things are also there. So this is script B. Now what can I say about script B? I have already said that script B is not same as the collection of all subsets of AB. There are subsets of AB that are not in script B. So what can I say about script B? I know that all these things are in script B, unions of intervals are in script B, the set of all rationals in AB is in script B, set of all irrationals are also in script B. So can I give a better description, a more comprehensive description of this set script B? For one thing, script B must contain all the intervals, because that's what we started with. So the starting thing is of course there. Then we added further things. The second point is that script B must be closed with respect to countable intersection, union and complementation. Now what does it mean? Suppose I take some sets B1, B2, etc. and form their union. So is it possible that BIs, they are all in script B, but this is not in script B? Of course not, because remember how we did it. We took all those things that can be constructed by using union, intersection and complementation repeatedly. So if already we have arrived at the BIs, then we will of course take their union in the next step. So this must also be in script B. And similarly, if instead of union I take intersection, a similar statement can be made. Whatever these things are, their intersection must also be in script B. If some set is in script B, we can also manufacture its complement, and that will also be in script B, because script B is the collection of all subsets that you can arrive at using these operations repeatedly. The third condition is somewhat more difficult to understand. It says that script B must be the smallest collection subject to these two restrictions. In other words, if you can give me some collection which contains all the intervals and it is closed with respect to countable set operations, that must contain script B. Now what does it mean? It is actually quite intuitive. When I said collection of all subsets that may be created using these operations starting with the intervals, this means initially you had nothing but the intervals in your basket. and you just manufacture things using the intervals. Do not take anything from outside. Now, if you put something from outside, then also it will contain all the intervals, because you have not thrown anything away, you have put some extra stuff. And of course, because you are manufacturing like this, so it will be closed under the operations. But that is not our script B, because you took something from outside. This condition says that you have to use the subsets that you manufacture starting with the intervals and nothing else. This condition guarantees that nothing else. So script B must have these properties. Now this collection script B has a name. It is called the Borel sigma-algebra on AB. Borel sigma-algebra. In fact, just this condition is called sigma-algebra. So script B is a set which is closed with respect to countable intersection, union and complementation, and we might also add non-empty, because if you just take the empty set, then also this is closed under everything, because there is nothing, so vacuously closed under everything. So if you take any non-empty collection which satisfies this, you call it sigma-algebra, and these two conditions give it the adjective Borel. Borel sigma-algebra. In this exercise, I am giving you two sigma-algebras, not necessarily Borel sigma-algebras. So, just any two collections which satisfies this condition. They are non-empty and they are closed with respect to countable intersection, union and complementation. Your job is to show that the intersection, that is collection of all sets which belong to both B1 and B2, they also forms a sigma-algebra on AB. So you have to prove that.